Hi everyone. So today's section is about the fundamental theorem of calculus. As the name suggests, this is actually the fundamental theorem of long calc 1 and long calc 2, and actually of all calculus. So this actually explains a very powerful relation between derivatives and integrals, and it's going to give us a powerful tool to compute definite integrals without using geometry or Riemann sums as we've done so far. So the goals of this section are, so first, to state the fundamental theorem of calculus, part 1. So sometimes we'll just say FTC1, it's just shorter. And then there's a second part to this theorem. So we're going to state the fundamental theorem of calculus, part 2. And we also call this FTC2 for short. So we're going to use FTC1 and FTC2, and we're going to show how useful this theorem is. Both parts are in examples. So use FTC1 and FTC2 in examples. Okay, and then we're going to explain a powerful relationship between differentiation and integration. Let's say differentiation and integration. Now we're not going to prove the fundamental theorem of calculus, even though it can be done, not in a very hard way. We're going to first state a theorem, which is sort of the mean value theorem for integrals. So we know a mean value theorem for derivatives. There's also a similar one for integrals. Before I do that, let me just point out here that so far we know two ways of calculating definite integrals. So basically using geometry, and 2 using Riemann sums. So limits of Riemann sums. Okay. Now, of course, using geometry is nice but limited, because if you have very complicated shapes, it's going to be hard to compute the area, and the limits of Riemann sums is also very powerful, and this is comprehensive, so you can define a priori any definite integral using limits of Riemann sums, but this is usually hard. Okay. So in this section, the fundamental theorem of calculus will give us a very powerful way, a new way of computing definite integrals. So in this section, the fundamental theorem of calculus part 2 actually gives a powerful way of calculating definite integrals. All right. So let me start by first stating the mean value theorem for integrals, which is actually useful if you want to prove the fundamental theorem of calculus. But for now, we're just going to give it as a theorem and maybe do an example or so. So the mean value theorem for integrals. Okay. So let's suppose that f is a continuous function on the closed interval a comma b. So let f be a continuous function on the interval a comma b. Then there is, of course, at least one c in the interval a comma b such that the following happens. Okay, so the value of the function at c is equal to the average value of the function, which is 1 over the length of the interval b minus a times the integral from a to b of the function f dx. Okay, or in other words, you can state this as you can say that the integral from a to b of f of x dx. So this is some area, right, with signs, but this is equal to the value of the function c times b minus a. So this is the right-hand side now is the area of some rectangle, and this is the area under this complicated curve. Okay, so let's do one example. So maybe I should write this down. So this is area of a rectangle. Okay? So let's do one example. Let's find c in the interval 0, 4 such that f of c is the average value of the function. If the function is 8 minus 2x, okay, so remember that the average value of the function is 1 over 4 minus 0 times the integral from 0 to 4 of this function. So this is equal to 1 over 4 times the integral from 0 to 4 of the function is this function here. So 8 minus 2x dx. Okay. So if you want to calculate this, we have to use geometry. You can actually use also the Riemann sum, but that's going to be a longer process. So let's just use geometry. Okay. So here is x and here is y. So when x is 0, we have that y is going to be 8. And when x is 4, you have that y is 0. So you have 4 here and then 8 here. So it's this line segment. Okay. So we want to find the area of this, the area of this triangle. Okay, let's do that very quickly. So back here to the integral, so I have 1 over 4 times the yellow area. Let me just say yellow area here. So this is 1 over 4 times, well, this is a triangle, so I have 4 times 8 over 2. So these cancel, so this is 4. Now this means that the average value of the function is 4. Now of course if you set this equal to c, f of c, sorry, so f of c is equal to 8 minus 2c, which is now equal to the average value, which is 4. So then you get that c is equal to 2. Okay? So c is an x value. So c is somewhere here between 0 and 4, so it's in the middle. So c, which is 2. Now this means that this is the average value, or f of c, okay? And according to the mean value theorem, this area, which is the yellow area in our example, should be f of c times b minus a. So it should be the following area. Okay, so the yellow area is basically, according to this theorem, this blue area. So it's the area of a rectangle. So you can do this for any function. So the theorem is telling you that the area of under any curve, as complicated as it can be given just as the area of a rectangle. Okay, and as I said, this is a very important theorem if you want to prove the fundamental theorem of calculus, which I'll state now in a second. All right, so let me state it now. So this is the main theorem of actually this entire course. Let me just say main theorem. So this is called the fundamental theorem of calculus. Okay, so I'll state both of them at the same time. Okay, so just give me 1 second. Okay, so there are two parts to this theorem. So part 1 says the following. If you have a function f which is continuous on a closed interval a comma b, and the function g is defined by the following definite integral, the integral from a to x of f of t dt, okay, then this function is this function g is continuous and differentiable. So g, then g is continuous on the closed interval a comma b and differentiable on the open interval a comma b, and moreover the derivative of g is just f. In other words, the derivative with respect to x of the integral from a to x of f of t dt is just f of x. Okay, that's the first part. And the second part says the following. So I have the same conditions on f. So f is continuous on the closed interval a comma b, and capital F is an antiderivative of lowercase f, capital F could be any antiderivative. Then we have the following. So the integral from a to b of little f is equal to the following. So you have this notation, capital F, you put this vertical line, and then you say a and b like that. And this means this is equal to f evaluated at b minus f evaluated at a. So this means, so the second part means that the definite integral is the net change of an antiderivative of this function little f. Okay, so the short version of this theorem, so if you just want to write this shortly, say FTC 1 and 2 is the following. So this is what most people remember. So there are two parts. So part 1 and then part 2. So the first part says that the derivative with respect to x of the integral from a to x of f of t dt is equal to f of x. And the second part says that the integral from a to b of little f is the net change in an antiderivative. Okay, so let me explain this on a picture. At least part 1, I'll explain it on a picture. And then I'm going to write some sentences related to these two theorems. Okay, so the first part, first of all, says that the derivative of an integral is the function. So that basically a derivative and an integral just cancel each other. Okay? So they're inverse processes. But let me explain now part 1 in terms of areas. Okay, so let's suppose that the following is the graph of our function. So I'm just going to draw a generic graph. So always draw that. Okay, so let's say this is A and this is B. Now x is somewhere between A and B. So x is between A and B. And t is between A and x. So for example, if x is somewhere here, okay, then t should be in this interval. Okay, so let me use some colors here to make this a little more concrete. Oops. Right, so let's suppose this is the area on the right of x, and this is the area on the left of x. Okay. So the integral here is this blue area. Okay, it's this blue area here. Now this first part here, FTC1, says that as x moves to the right or to the left, the rate of change of this area is exactly equal to the value of the function, which is this, right? This is f of x at that point. So as, let me just write this on the picture. So as x moves to the right or to the left, then the rate of change of the blue area is equal to the value of the function f at x. Okay, so maybe I should also say that this function here is the function f. Okay. So this means that, let me write this again in sentences. So FTC1 means that the rate of change of the blue area is f of x. Okay, and FTC2, the second part, says that the definite integral of f, of little f, is the net change of the antiderivative capital F. All right. So now I hope this is clear. Let's do some examples. So I'll start with examples from FTC1. All right. So for example, if you have that, you want to find the derivative with respect to x of the integral from 0 to x of t squared plus 1 dt. According to this theorem here, if you have this derivative and this integral with these limits of integration, now this t is different from this x, they're not the same, okay? So all you need to do is drop all of this and then replace this by x, okay? To get this f of x here. So I'm going to drop all of these because I have x here and a constant here, and I'm taking the derivative. And then the answer is just by plugging in x for t. So basically the answer is x squared plus 1. And this is by the fundamental theorem of calculus, part 1. So it's that easy. So you don't really need to compute this, okay? You can just use the FTC to omit these two parts. Okay. Or another example would be the derivative with respect to x from 0 to x of any function that you like. For example, ln of t dt is equal to, for the same reasons, you just make this t here, you make it x. Okay, so then the answer is ln x, okay, by FTC 1, sorry, by FTC 1, and so on. Now what happens if you don't have, okay, so let me go back to this theorem again, FTC 1. So you can use this theorem only if x is above here and down here you have a constant, okay? And if, for example, x is down here and then a is up here, you have to do something else. Instead of x, if you have, for example, a function of x, you have to do something else. And if you have a function of x here and a function of x here, you have to do something else. So let's do some examples related to those scenarios. So for example, if you have the derivative with respect to x of the integral from x to 5 of 1 over t to the power of 4 plus 3 dt. And the problem here is that x is down here and 5 is up there. So I have to bring x up here, which means, according to the rules of or properties of definite integrals, if you switch 5 and x, you have to multiply the whole thing by minus sign. So I have minus the integral from 5 to x of 1 over t to the power of 4 plus 3 dt. Okay? So now you can bring the minus outside of the derivative because that's one of the rules of differentiation. So I have minus the derivative with respect to x of the integral from 5 to x 1 over t to the power of 4 plus 3 dt. Now we can use the fundamental theorem part 1. Okay, so according to FTC 1, this derivative should equal 1 over x to the power of 4 plus 3. That's it. Okay, see, we just made this t here an x. Okay, I hope this is clear. So we just said that if the constant and the x are switched, you have to switch them back and you have to multiply by a negative sign. Okay. Now what if you have, for example, a function instead of x. So what if you have the derivative with respect to x of the integral from -1 to x to the power of 7, for example, of cosine t dt. Okay, so here you have to use the chain rule. Okay, so the derivative is equal to, okay, wait a second, so I wrote something wrong here. This should be cosine t. Oh, this is fine. Let me just erase this and write without parentheses dt. Okay, I didn't need the parentheses there, sorry about that. So this should be cosine of whatever you have up here. So you just put this instead of t, and then you have to take the derivative of x to the power of 7. So cosine of x to the power of 7 times the derivative of x to the power of 7. Okay, that's the chain rule. So this is equal to cosine x to the power of 7 times, according to the power rule, 7x to the power of 6. Okay. So whenever you have a function here instead of just x, then you always use the chain rule. Okay, don't forget that. But the function should be up here, and this should be a constant. Okay. Now what happens if you have a function up here and down here? Okay, so let's do a question like that. So let's suppose we have the integral from x to x squared of root t plus 1 dt, and you want to find the derivative of this. So obviously we have to use some sort of FTC1, but first we have to split this into two pieces. Okay, so let's suppose that here is x and here is x squared, and maybe there is some 0 here in between. Actually, for instead of 0, you can choose any point. You can say a constant a. Okay, if you just say a, that's fine. But let's choose 0. Let's suppose that 0 is between x and x squared. Then you have the derivative with respect to x of the following. So according to the properties of integrals, you can first integrate from x to 0, and then from 0 to x squared, and add the two things. So I have the integral from x to 0 of root t plus 1 dt, plus the integral from 0 to x squared of root t plus 1 dt. Okay, so now you can take the derivative of the first plus the derivative of the second. Okay? But now since 0 is up here and x is down here, I have to switch x and 0, okay? And I have to multiply by negative sign. So this is equal to the derivative with respect to x of minus the integral from 0 to x of root t plus 1 dt, plus the derivative with respect to x of the integral from 0 to x squared root of t plus 1 dt. Okay, so now you can take this negative sign outside of the derivative, and here we have to use the chain rule. Okay, so let's do that. So this is equal to minus root x plus 1. This is just FTC1. Plus root of, now instead of t here, you put x squared, so you have x squared here. So I have x squared plus 1 times the derivative of x squared. So times 2x. Okay? this is now FTC1 plus chain rule. Okay. So I hope this is clear. So these are all the scenarios that you can have. You can either have x at the bottom and a constant at the top, which means you have to flip, or you can have a function at the top instead of x, which means you have to use the chain rule, or like in this example here, you have functions both top and bottom for the limits of integration, which means you have to split into two pieces, assuming there's a constant in between x and x squared, and then do the necessary work after that. So use FTC1 and the chain rule. All right, so now let's do some examples concerning the second part of the fundamental theorem, so FTC2. So examples, and this is about FTC2. All right. So for example, let's start with an easy one. So if you want to take the integral from 0 to 2 of x squared dx, this is equal to an antiderivative of x squared from 0 to 2, and an antiderivative of x squared is x cubed over 3 from 0 to 2. Of course, now you may ask, why don't you add a c here where we don't need c, okay? Let me just say we don't need c, okay? The answer will be the same for any choice of antiderivative. So let's just choose an antiderivative without a c. So this is equal to 2 cubed over 3 minus 0 over 3. So this is 8 over 3. Okay? So let's do another one. So let's do the integral from -1 to 3 of a longer polynomial. Let's say I have 1 minus 3x. Let me do 1 minus x minus 3x squared to have a nicer looking antiderivative. So this is equal to, okay, so you can do the antiderivative of this function here, which is antiderivative of this plus antiderivative of that, and then antiderivative of that. So you can do now x minus x squared over 2 minus 3x cubed over 3, right? That's the antiderivative of this function. And now you have to evaluate this at -1 and 3 and then find the difference. So this is equal to 3 minus 3 squared over 2 minus 3 times, by the way, these cancel, so 3 cubed minus 1 minus 1 over 2 minus 1. Okay, and if you add these, you'll find, well, let me just simplify this. So I have 3 minus 9 over 2 minus 27. So these two cancel. So I have plus 1 over 2. So I have negative, so I have 3 minus 8 over 2 minus 27. So this is minus 28. All right. So let's do another one. So basically with these questions, as long as you know the antiderivative of the function you're integrating, you can just do the antiderivative evaluated at the top limit minus the antiderivative of that evaluated at the lower limit of integration. Okay, so let's do another one. So the integral from 0 to pi over 4 of sine t dt is equal to negative cosine t from 0 to pi over 4 and this is equal to minus cosine of pi over 4 minus cosine of 0. So this is equal to minus root 2 over 2 plus 1. So this is 1 minus root 2 over 2. Now I have to warn you here because you cannot do this at free will, okay? So warning. If, for example, you have, let's say, the integral of, let's say from -1 to 1 of x to the -2 dx, then you'd say, of course, I can do the power rule for integration, so x to the -1 over -1 from -1 to 1, so this would be 1 over -1 minus, then you have -1 over -1, so this would be -2. While this is wrong, since the function 1 over x squared, or x to the -2, is not continuous at 0, and 0 is a point in the interval from -1 to 1. Okay, so since y is equal to x to the -2, which is 1 over x squared, is not continuous at, I mean on the interval, let me say on the interval, not at, on the interval -1, 1, right? Because if you plug in 0 here, you get 1 over 0, which is not good. Okay, so you have to be careful. Now you can integrate these functions also if you have, for example, a variable here. Okay, you can also do that. So for example, let me do one more example here. So 4 So if for example, if you want to integrate from 1 to x cosine t dt, then an antiderivative of cosine is sine. So sine t from 1 to x. So this is equal to sine x minus sine 1. Okay, so that's it. So don't be distracted by having some x here. As long as this x is unrelated to this t here, you can always do this integration. Okay. All right. So now let's do an application. All right. So let's do, for example, the following application. So let's suppose that you have an object suppose an object moves in a straight path with velocity function let's say v of t. Let's pick an easy one for now. So t squared minus 1. And let's suppose that time is positive or 0. Okay. And the first question is find the displacement, and the second question is find the distance traveled on the interval 0, 3. So from time equals 0 to time equals 3. Now, whenever I talk about remember, whenever I talk about distance traveled or displacement, and I'm given the velocity function, I always have to do integration of the velocity function on a closed interval. So the first question is find displacement of this object during the time interval is 0, 3. And displacement is equal to just the integral from 0 to 3 of the velocity function so, dt. So this is equal to the integral from 0 to 3 of t squared minus 1 dt. Okay? So this is equal to the integral of t squared minus 1 is t cubed over 3 minus t from 0 to 3. So if you plug in these, you have 3 cubed over 3 minus 3 minus 0 over 3 minus 0. So this is equal to 6 units, okay? Now this is if you do the displacement. Now if you do the distance traveled, sorry. So if you want to find distance traveled, let me say the total distance traveled, maybe that's better. The total distance traveled during the time interval 0, 3. Then we have to find the integral of the absolute value. Okay? So the distance traveled is equal to the integral from 0 to 3 of the absolute value of Vt. This is always true for any velocity function. So from 0 to 3 of the absolute value of t squared minus 1 dt. Now of course this means that we have to find where the velocity function is positive and where it's negative. Whenever it's negative, you have to multiply it by negative 1 to make it positive. So for example, in this case we have if you draw the graph of y is equal to t squared minus 1, then you have this graph, right? More or less. So this is negative 1, and then 1. Let's say this is 3. So basically from 0 to 1, this function is negative, and from 1 to 3, it's positive. So this integral is equal to the integral from 0 to 1 of minus t squared minus 1 dt plus the integral from 1 to 3 of t squared minus 1 dt. So whenever the velocity whenever the velocity is negative, you have to multiply it by negative sign to make it positive. And in this case, it happens on the interval 0, 1. Okay, so this is equal to minus t cubed over 3 plus t from 0 to 1 plus t cubed over 3 minus t from 1 to 3. Okay, so if you now find these integrals, this is equal to minus 1 over 3 plus 1 minus 0 plus 3 cubed over 3 minus 3 minus 1 over 3 minus 1. And if you add these numbers, you'll find 22 over 3, and of course this is bigger than 6. Okay, so in general, the distance traveled, or let me start with displacement. So displacement is equal to the integral from a to b, this is the time interval, of the velocity function, and the distance traveled is equal to the integral from a to b of the absolute value of the velocity function. Okay, so just be careful there. All right, so this is all I had to say about 5.3. Now you can work on your own and do some more examples. Thank you.